Hello dear students. In this video I'll be talking about more about basically Heisenberg's uncertainty principle, how this principle leads us to the zero point energy of the particle. Now, say for example, if we have a classical particle and we'll boil down that particle to the lowest possible temperature for the sake of argument. Now, this particle will not it will have zero energy. Its all motions will cease. It won't have any energy. But the quantum particle does not behave exactly the way the classical particles do. So we here in this video would like to see that how, of course, the calculations will be very crude. You'll see that this how this uncertainty principle leads to the zero point energy of the particle, which is not the case with the classical particle, which is not the case with the classical physics. So in the domain of classical physics, the particle must have it must have zero energy at that very state where we can assume that state to be the lowest possible state of that particle. Now, to go with that idea, what uncertainty principle says is that the product of uncertainties of, say, delta p is the uncertainty in the measurement of the position of the particle, a microscopic particle, and delta x is the uncertainty in the measurement of the position of this quantum particle. Then the product of the two is not zero. This product is greater or equal to h cross by 2. So, to translate down this uncertainty principle into some other simplest format, what it means here is that we cannot simultaneously measure the momentum and position of a quantum particle simultaneously. Now, and these uncertainties, if you have less uncertainty in the measurement of the momentum of the particle, then the uncertainty in the measurement of its position is going to increase, and vice versa. So we can crudely write down this delta p delta x nearly equal to h cross by 2. Now, choosing a quantum particle and an ideal quantum particle and writing down the total energy, it will be nice if we choose this particle as a harmonic oscillator, because we understand that the oscillations that can be set up, provided their magnitudes are small, then we have a correlation between the force and the displacement of that oscillation with respect to the mean position. Assuming these displacements to be extremely small, and certainly such kind of approximations as oscillators work out in different domains of physics. So here we are choosing a harmonic oscillator problem, and we want to measure the lowest possible energy for this quantum particle, choosing this quantum particle having harmonic oscillations. So our system is perfectly ideal. It's an ideal system, and we can think of the total energy of this system as E is the kinetic energy of this particle plus the potential energy of this particle. And so this E refers to the total energy of the particle, and K is the kinetic energy, and P dot E is a representative of the potential energy. So moving from here, we can write down this energy. This E is, we can think of this as 1/2 of mv square plus we have the potential energy of the harmonic oscillator was that's 1/2 kx of square, and we understand that how we get this m omega square x square. So this is the potential energy of this particle, and this is the kinetic energy of this particle, a harmonic oscillator. So this energy can be written as mv whole square by 2m plus 1/2 of m omega square x square. Now this mv, as we understand, this is momentum, so we can have momentum square by 2m plus 1/2 of m omega square x square. So this is our total energy for this oscillator, and P is the representative of the momentum, and X is the representative of the position of the particle. So if we think in terms of Heisenberg's uncertainty principle, then we certainly can we can utilize this P. This P will be h cross by 2x. So we can use for momentum, because we have delta P delta x nearly equal to h cross by 2, so we can choose Px equal to h cross by 2. So this P can be replaced by h cross by 2x. So using the value of this momentum in this equation, what we're going to obtain is E will be, it will be P squared by, oh, let me use another page. So this is my page 2. So I will have the total energy, E. So instead of P, I'm going to use h cross by 2x. So I will have h cross squared by, then 2 is there, then m is there, and 2 square is 4, and then there is x square, then plus 1/2 of m omega square x square. All right, so let's make it symmetrical. So this is h cross square by, this is 8 mx square plus 1/2 of m omega square x square. Now, what we are looking here, we are trying to measure the lowest possible energy of this particle which is oscillating in an ideal situation. So in order to calculate that minimum possible energy, what we got to do is the derivative of this equation should be with respect to x, that should be 0. So for E to have minimum value, we must have the derivative of energy with respect to x must be equal to 0. So for that purpose, what we are going to do now is we will differentiate the right-hand side of this equation. And on differentiating the right-hand side, the left-hand side is automatically 0. So we will have that minimum possible position of the particle that we are talking about here. So in doing so, what we will have differentiation of this thing. So this is h cross squared by 8m. So this will become d by dx of x raised to power minus 2, then plus 1/2 of m omega square d by dx of x square. Okay, I think till now it's fine. And now this thing should be equal to 0. All right? So if I differentiate this, this is h cross square by 8m. So this is minus 2 x raised to power minus 2 plus minus 1. All right? Then plus 1/2 of m omega square 2x. This 2 and 2 will go. And what will we obtain from here is h cross square by, so this will give me, this is going to give me 2 1s are 2 4s are. So this is h cross square, okay, this is h cross square by 4, that 2 minus 4m x cube, then plus 1 by 2m omega square. 1 by 2 is gone, so it is m omega square x is equal to 0. And we can write down this m omega square x is equal to minus h, it will become plus h cross square 4m x cube. This should be the case. Yeah, this should be the case. Okay, so this is going to turn on this side, so the negative will become positive, and we can have this x will become x to the power of 4, and I will have h cross square on the right by 4m square. So m times m will give me m square, then omega square. Okay, now this is x raised to power 4. Now, if this is x raised to power 4, and this is the square of this, so we can write down this as h cross square by 2 square m square omega square. So I can write this as x square whole square. So we can turn down this square on the right hand side, and square and all of these root and squares will cancel. So I have x square equal to under root of h cross by 2m omega. This whole square and root will cancel. And finally, we'll have x is under root of h cross by 2m omega. So this is our minimum possible position. So this is our minimum possible position, and for where we achieved it, we obtained it from taking this condition that the derivative of we'll have this minimum possible energy if we take the derivative of this energy with respect to the position equal to 0. And in calculating the energy now, so if I have to calculate its energy, so I can use this energy is what is that equation? Yeah, where I have to use the value of this minimum x that we have obtained from this equation. So I can use for the x that I have obtained now. So what will be that, and see what will be the result that we'll be obtaining from solving this equation. So this is h cross square by 8m x square. So x square means under root of h cross by twice m omega whole square. And then we have plus 1/2 of m omega square. Then we have again x square. So we would like to multiply under root of h cross by 2m omega whole square. Now let's see what's going to happen here. We are going to cancel the square and root, and this m and m will go. This h cross and square will go. And anything else here, square and root will go, this square and omega will go. So E will be, not sure what we'll obtain here. This E will be h cross by, okay, here I have 8, so this 2 is 2 ones are 4, so this is h cross by 4. What is left over here is omega. This is divide by omega basically, so omega will come on the top. So this is omega. Plus, okay, this m and m is gonna go, so we will have again h cross omega divide by, okay, this is 2, so this will give us 4. Okay, so we have obtained this minimum possible energy for this quantum particle. So this E minimum is, so we'll have 4, then we'll have twice h cross omega. 2 ones are 2 twos are h cross omega by 2. This is the minimum possible energy for this particle. So this energy is called as 0-point energy, and we have seen, we have at least obtained an equation that tells us that these quantum particles they have the so-called the minimum possible energy, and this minimum possible energy is called as 0-point energy.